So what is a parametric set of equations? Okay. Curves that are defined parametrically. What is the purpose of that? For instance, let's say that I have x of t is equal to t plus 2. And we have y of t is equal to t squared plus 3.
It shows when two dimensions, two axes, are the dependent variables of a single other independent variable, in this case t.
That's very good to recognize, is that we're actually defining x and y separately as dependent variables of a variable t. And what would be the importance of doing that? Why not just, work with our, standard functions of y and x that we're so familiar with? Why end up, changing things all of a sudden to now include this new variable? What would be the purpose of this?
Well, my first thought, and this would probably become better if you threw in a z-axis, but it would be position in relation to time.
That's exactly what the point is. And this is the most important section in Calculus 2 for moving forward into Calculus 3. So understanding parametric curves is the critical aspect of Calculus 3 or multivariable calculus. Because everything that we do, 70% of what we do in Calculus 2 or in Calculus 3 is going to refer to parametrically defined curves. Okay. And the idea here is that it's saying that if you give me a t, picture t as being time, even though t doesn't always need to be time. If you picture t as being the independent variable, that means that you give me a time, and I'll be able to tell you where I was in the horizontal direction and separately where I was in the vertical direction. So all I'm saying is you give me a time, and I'll tell you an x and a y. So this really describes not only a curve, but it describes motion along a curve. So, oftentimes we could come up with some different values. We might think, let's create a chart here to where we end up picking some t values, and we find the corresponding x values, and we find the corresponding y values. You could pick negative t's, you could pick positive t's. So let's pick maybe -2 for t, -1, and 0, and 1, and 2. And you could obviously pick more if need be, but essentially what this is saying is you plug in -2 for each of these. And so let's just plug in -2 for the x equation. So if I plug in -2, x is found by just adding 2 to the t value. So that would mean this is 0. Add 2 to -1 to get 1. Add 2 to get, add 2 to 0 to get 2. Add 2 to 1 to get 3. Add 2 to 2 to get 4. And you should now notice a pattern in the x's, 0, 1, 2, 3, 4. That's a linear change, which makes sense because x changes linearly. Now we see that the y coordinates are going to be dependent separately on t as well. So now if I look at the certain t coordinates here, it's saying to square the t, then add 3. So square -2 to get 4, add 3 to get 7. Square -1 to get 1, add 3 to get 4. Square 0 to get 0, add to get 3. Square 1 to get 1, add 3, and you get 4. Square 2 to get 7, or 4, add 3, and you get 7. So now we should realize that this changed quadratically, right? The y coordinates changed in a quadratic way. So all we're basically showing here is that we should be able to graph this or come up with some sort of plane curve that basically describes this situation, okay? So just go ahead and draw a graph then. In this particular problem, you could see that you actually don't have any negative x and y values. So I really only in this particular problem need to be graphing in the x and y direction. Okay. Let's go ahead and plot these points. Okay. So I need to make sure that I go out to 4 in my x direction. 1, 2, 3, 4. And in my y direction, I need to be going 1, 2, 3, 4, 5, 6, and 7. There's 7, there's 3, there's 4. And so now I can actually draw my plane curve. But notice what I'm going to do as I plot my values. So I could see that when t is equal to -2, I'm at this point right here. But I'm not only just going to plot that point, I'm going to plot the fact that this is what occurs when t is equal to -2. It's important to label because the whole purpose of a parametric curve is to demonstrate when I was at a particular location. Not just where am I, but when am I? Okay. So notice in the next one, I plot 1, 4. 1, 4 gives me right here. But I don't just plot 1, 4. I plot when I got there. That's at t equals -1. Next point we plot is 2, 3. So we plot the point 2, 3. And there I am. But again, this is when t is equal to 0. When I plot 3, 4, or I get right up here, 3, 4. And now I could see that that occurs when t is equal to 1. And finally, when 4 gets 7. And this is when t is equal to 2. So one of the most important components of graphing a plane curve, we refer to this as a plane curve, is that we are labeling with the indicated t values. So that now when I end up drawing this, it looks like this right here is my curve. So it looks to me to just be a parabola. There was no way for me to tell exactly what the plane curve is going to look like necessarily. I mean, you could kind of, this was a really simple one because it's a quadratic and a linear. But notice that there's not ever really a simple way automatically to know what the plane curve is. But one thing we're able to do is determine what is the formula for that. Now, one thing that I forgot to put on here that's important here is to indicate the direction that we're moving in. So that's why I shouldn't typically put arrows on here. Okay. I wish there was a way for me to just erase parts of that, but whatever. It's really bad. Pretty hard to draw curves on here. Okay, so don't put arrow tips on the ends of these like this, because that indicates that it is going infinitely in both directions. But what we want to do instead is we want to put arrows on the actual curve, pointing in the direction of motion. So notice as t increases, what I'm really doing is moving in this direction. So the plane curve is showing me that I'm moving along this path, this pink path, but the points are indicating when I actually got to each point on that path. So I can actually see a lot of things going on. I could see the velocities, I could see the steepness, which is the, if I look at the steepness of the curve right here, then that would be the velocity. I could see that I moved this far in 1 second, but then in the next second, I moved further. That tells me that I'm accelerating, and I'm going to be able to actually find out what my acceleration is at different times. I'm going to be able to find arc length, which would tell me the distance that I traveled between 2 times. So essentially, the entire purpose of a parametric curve is to demonstrate where I am, but also when I got there and the direction that I'm moving in. Okay? So the last thing we're going to do, just as a little review of parametric equations, is that you could also eliminate the parameter. The parameter in this case is t, because I'm saying that x is dependent on t, y is dependent on t, so the parameter in this case is t. So how do we eliminate the parameter? What do you think we do there?
We have to find what t is with those equations.
Yeah, so let's find t in terms of one of the variables. It doesn't matter which one. And then once we do, we plug that into the other equation, and then we should only have an equation with y's and x's. So we're going to start off over here with x equals t plus 2, because it's the easy one to isolate t. That means that t is equal to x minus 2. Okay. Well, then I look over here and recognize that y is equal to t squared plus 3. But we know that t is actually x minus 2. So I can plug in that x minus 2 for t. And notice that I get that y is equal to x minus 2 quantity squared plus 3. And that's the actual function. So the plane curve could be described by that function. The problem is, if I just eliminate the parameter and graph this function, which unsurprisingly is a parabola shifted right 2 and up 3, shifted right 2 and up 3, it's just a parabola shifted over. The problem is, if I eliminate the parameter and graph it, then all I have are points. What I don't have are the times that it took me to get there. And so one of the most important aspects of a parametric set of equations is the fact that t describes when I got to a certain location. All right, so everybody remember that? All right, so we're just going to go ahead and go through the calculus of this then, because what we're really trying to do at this point is let's say you've got this plane curve, and I want to start to find derivatives. Derivatives telling me slopes. Or maybe I want to find arc lengths because I want to find distances that we traveled. Okay, then I can do all of that simply by doing a little bit of calculus with these parametric equations. Okay, so a couple of things to recognize here. And so we'll go ahead and pull up the lecture notes and we can just kind of move through some of those. So let's just say that you have two different curves, and this is the standard way to write, parametric sets of equations. You would label x as being f of t, and you would label y as being g of t. And in calculus 3, if we have a z coordinate, we would call it h of t. Okay, but in this case right here, notice that we could eliminate the parameter by converting this into y equals some other function of x, which is really what we just did in that last problem. Okay. So what we want to do here is we want to use this fact that we could eliminate the parameter to now find a way to find the derivative without having to actually eliminate the parameter. In other words, how could I, instead of knowing that the function is x minus 2 quantity squared plus 3, how could we find the derivative or the slope by only using the x and the y parametric curves? Okay.